Alright, this video covers section 3.4 concavity and a second derivative test. This video specifically is just going to talk about concavity. Alright, so as we move into this next section, before we even get started, I wanted to kind of look at this picture with you. The idea, if we had some company X and we had a graph of their advertising spending, you can see that the x-axis is representing the advertising money and the y-axis is representing net profit. Typically, not always the case, but typically when you first start spending money on advertising, your net profit is going to start to increase slowly. And then as you spend more money, it'll start increasing more quickly. And there's going to reach a point where it's kind of increasing at the highest rate, or the slope is the most steep. As you spend more advertising money, people can only buy so much, so your net profit may increase, but then it will start to slow down. So this idea of concavity is really important because it could give us kind of that point where our slope is the steepest, or our rate of change for the amount of advertising money in relation to the net profit is the steepest. So today we are going to look at the idea of concavity. And concavity relates to the second derivative because basically it's going to be the rate of change of the slope. So the question that you may want to ask yourself is the slope increasing or decreasing? So you're going to either have a graph that is concave up, and I always describe concave up as it's the idea that it's facing upwards and it's like a bucket or something like that. It could hold water. Okay, draw a graph of it for you here. So something is concave up. Graph is facing up. Okay. And the way that we can tell it's concave up analytically or algebraically here is if our second derivative, so f double prime of x, is greater than 0 on some interval a comma b, then f of x, our original function, is concave up. Concave down is going to look the opposite, so I'm going to say it does not hold water. Okay, if you were to draw a graph of it, it looks similar except that it would be facing down. Okay, so I'm going to show you a PowerPoint, kind of give you some ideas about these graphs. So you can see here's our function, and let's see, oops. Here is the graph of our original function, the line in red. So as you look at this, make some observations. Maybe think about where you think, well, first look at the first derivative. So think about where the slope is 0, where the slope is increasing or decreasing. Okay, so maybe kind of make just a mental estimation of what that first derivative graph is going to look like. So here is our first derivative. Hopefully it should not surprise you. You can see that at x equals -2, the first derivative is 0 because the red line, our original function, was 0. At x equals 0, you should be able to see that the first derivative, the line in blue, is 0 because the slope was 0 for our original graph. And the same thing holds true for x equals 2. You can also look at the intervals of increasing and decreasing and see that the first derivative y values are going to be positive or negative. Okay. Now the second derivative is going to represent concavity of our original function, so whether the graph is concave up or concave down. And it's going to also show the slope of our first derivative. So take a moment, kind of think about some areas, what that graph might look like. so here is our second derivative graph, the line in black. Okay, so hopefully you can see that graph starts out as concave up, and then when we get to about negative 1.2-ish, it's going to change concavity, so the second derivative has a 0. And then the red graph is concave down for a while. So then at x equals 1.2-ish again, you're going to see that the second derivative has a 0, because our original graph then changes to be concave up. So hopefully you can kind of see some of the connections there. And just a note here, we want to add on for something if f double prime of x is less than 0 on our interval a comma b, then f of x is concave down. All right, with concavity, concavity should be Roman numeral 1. The second point underneath this is we're going to look at a little bit is inflection points. And basic idea of an inflection point is where a point where the concavity changes. Okay, we have potential inflection points. And I call, the short name for them I call pips. And basically they are where the second derivative equals 0 or is undefined. So if you look at an example, I'm going to ask you to find points of inflection and discuss concavity. Okay. So if I give you the function f of x equals x cubed minus 6x squared plus 12x. And we're going to do this without our graphing calculator, so we should be able to figure it out analytically. Okay, so the first thing you want to do is find your first derivative, which is 3x squared minus 12x plus 12. Okay. Then we want to go ahead and find our second derivative, because we're looking at concavity and inflection points, so we're going to get 6x minus 12. We want to find our potential inflection points, so that's going to happen at x equals 2. Okay. And I'm going to set up my chart, except now it's going to be with my second derivative. Go from negative infinity to 2 to infinity. Okay. Value that we could plug in that is less than 2 would be maybe 0 if I plug it back into my second derivative. You can see that my second derivative would be negative. Value greater than 2, maybe 3 if I plug it back into my second derivative, so then my second derivative would be positive. Therefore, we can make a concluding statement at x equals 2, our original function f of x has an inflection point because f double prime of x changes from negative to positive or changes sign. Okay, and then if you wanted to list concave up intervals, it would just be from 2 to infinity, and concave down would be negative infinity to 2. Okay, so that is it. Let me know if you have any questions.